My talk is called Considering the Uncountable. I've always been interested in the connections between math and art. In particular, I like to find the beauty in math and the truth in art. I find that these are universal languages that are connected through symbolism and structure, poetry and analysis. I've spent a long time discovering for myself some of the amazing things that they have in common. First as an artist, and later as a mathematics teacher. When I first came to New York from Chicago, I worked for an art shipping company, and I had a job as a truck driver, but it was a very elite service, and we went to collectors, museums, picked up art, sculpture, and then delivered it. So that was my background, and at the same time, I found that I could actually enjoy the labor. Like, I connected myself with physical things, making and building things, writing, painting. This is one of my works from, it's actually a work from a series called Celestial Navigation. This was done about 10 years ago, and it exhibited at the Butler Institute in Ohio. For this example, to me, connects art and math, because at the same time as that exhibit, I gave a lecture at the university and connected networks and Euler's graph theory with artwork like this, in a very loose, interpretive sense. Later, some of these ideas actually came together in the book that Bruce mentioned, recently published. It really focuses on the ideas of math and art together as symbolism and structure. So one of the perks of my job was that we got to go to every single exhibition in New York, all the major museums, for free, that you just got in. And this is the Italian sculptor Mario Merz that I met there at the Guggenheim. I had just delivered the exhibition, and here he is talking to me. Well, actually, I'm talking to him. And I don't know if he's actually in agreement with what I'm saying, because actually there's another picture where he's kind of like going like this to me and telling me what he really thought. But just after this was taken, he gave me a drawing in the museum. He had this interpreter, and he was like very enthusiastic, gives me a piece of paper like this. And so he drew the spiral and put some numbers on it, signed it, and there's my name with an I instead of an E. But, that's, part of it. For me, this is an example of how math and art are actually connected. He was a sculptor who put Fibonacci numbers into a lot of his work. And there they are, kind of loosely arranged. So like my own work, here was another example of how math and art could relate and speak to each other. Today, I'm very fortunate to have a place in the woods where I can continue to paint, continue to write, but I also really enjoy chopping wood. And this is my wood pile. You have to get ready for winter, if you know what I mean. It's like Game of Thrones thing. I also like to go into the woods and dig up rocks and pull them around and build things, like we have a stone wall. So while I'm doing this, I kind of lose track of time. Like, I really zone out, and hours can go by. Here's an example of my wall. But the string here is kind of like this axis. You actually use a string in order to build the wall to make sure it's the same height as you sort of go along. But that string is symbolically about this axis that doesn't move, but everything's moving around it. Okay, so I'm in this zone, and there I am out in the woods, and I'm building and everything like that, and everything is great. And I think that these non-traditional experiences have given me, I guess, a unique perspective on mathematics. In particular, I think it's given me like a holistic sense of life that I try to bring into my classroom when I can. I try to get my students to go beyond, oh, these are just numbers. Well, really, there's like a lot going on here with this stuff. It's a philosophical approach, and that's what I try to bring into my classroom. So when I considered writing a proposal for this symposium, my thoughts turned to a more abstract direction. Borders, walls, they can be political, social, economic, but I was more interested in this.
You shall not pass!
All right, that's very dramatic. It's Gandalf saying, you can only go so far and not take it any further. Right. So, this is the moment when I was in the classroom and had this actual, I guess it was an epiphany. I was teaching a lesson on the unit circle and the tangent function. And suddenly I was like overwhelmed with this idea. Let me tell you a little bit more about it. My idea was connecting the tangent function to cardinality. This is an idea that sort of like appeared to me all of a sudden, and I'm going to sort of go through this lesson and take you step by step and show you what I was thinking when this took place. When I am talking to my students about limits and end behavior of a function, I often approach this with just a basic question like, can you describe infinity? And some of their responses are pretty interesting. Beyond time, an unlimited amount of numbers, etc. This is an opportunity for teachers to really open up a discussion. These are opportunities for not the type of discussion that we often hear, which is, how am I ever going to use this in life? I want to take it like full circle, well, 180 degrees, to the other side and try to say, like, why not consider something like this? So we usually start off by drawing tangent. And here are the first quadrant values, right? The angle is increasing from 0 to 90 degrees as it approaches our so-called wall. This is the boundary now, the border, where tangent is undefined at 90 degrees. We like to say that the function begins pretty slowly. It starts to climb slowly. And then all of a sudden it takes off and quickly accelerates. Well, I do say quickly, but really it would take an infinite amount of time to reach the line that we can easily represent here with this dotted line. So I kind of think of this as the cosine, which is 0, gives you the slope that's all rise and no run at 90 degrees, which is very reminiscent to this. So if you're in a spaceship, of course, and you're approaching the speed of light, you get closer and closer, but that boundary, that border, is always just out of reach. It's kind of like you're running down a hallway or a tunnel, and you see the light at the end of the tunnel, and you're getting close to it, but for some reason the tunnel is expanding as you're running along, and it's actually getting away from you. No matter how far you run, well, you'll never quite reach it. So let's look at the tangent values for the first quadrant. Cosine and sine are represented here, and the tangent, of course, is the sine divided by the cosine. In other words, the slope of a line as it increases from 0 to 90 degrees. This image describes basically what's happening to the tangent. So we have the cosine and the sine as on the unit circle, and the tangent is represented as this line x equals 1. What's actually happening here is that the tangent is a straight line. It's 90 degrees, and every one of those slopes is mapped to this line x equals 1. In fact, there's a real number for every tangent, and the inverse of that as well. We can also see what happens as the line increases, the angle increases. It means that we have to stretch further and further to reach that tangent line. Even at 89 degrees, we're still only at the value of 57 on this number line. Where are all those other numbers? It's like you're looking into this interval, and like running down the tunnel, it's expanding as you go. You can get close to it. You can go to 89.9 degrees, but that only takes you to 573. It's like inside that boundary, it's really like the expanding tunnel. So this is the moment when I just had this time loss. Like where I was in the woods, chopping wood or moving rocks or painting or writing, all of a sudden, there was a cloud, in my mind, except for the pinpoint singularity that I was looking at here. And I thought, this was so strange. I looked at my classroom, I looked at my students, and I just said, don't you think that's weird? And everything was quiet. They were motionless. And I said, I think that's really strange. And they said, what's weird? What's weird, Mr. Deihl? Are you okay? Call the nurse. So I finally put the thoughts together, and this is what I came up with. Every positive number from 0 to infinity is represented in quadrant 1 by the tangent function, but exactly half of that section contains only the numbers from 0 to 1. So here's the math part. We have a function that's strictly increasing on the domain and has range values from 0 to infinity. But if you partition theta, the angle, to basically 45 degrees, it gives us tangent values of 0, 1, while the other half of the quadrant maps tangent theta to 1 infinity. That is all the rest of the numbers on that number line. Students will hopefully conclude or associate that because these two areas, 45 degrees each, are equal in size, so too must be the cardinality or amount of the intervals from 0 to 1 and 1 to infinity. This is an astonishing visual cue, and at the same time, it's an introduction to Cantor and his set theories. So Cantor was very much a philosopher who was somehow able to dive deeply into the abstraction of infinity, but somehow simplify it using his models such as diagonalization. With the following statement, I believe he personified mathematics and gave it a life of its own. At the same time, this is an example of maybe where poetry and philosophy meet mathematics. A set is a many that allows itself to be thought of as a one. Well, on a lighter note, someone recently at my school put the following item into my mailbox. It was either a teacher or a student, I don't know. But coincidentally, it really fits well with this presentation. Just give him whatever he wants. He's threatening to divide by 0. Thank you.